Simplifying expressions using rational exponents. In this video, I will go through several problems that can be solved more efficiently using rational exponents. In order to complete problems using rational exponents, you need some prior knowledge. The first is that we always rationalize the denominator. So if we saw the square root of 2 in the denominator, we would need to multiply by the root 2 over root 2, or a form of 1, to get 3 root 2 over 2. Keep in mind that a denominator is irrational if we have a base to some fractional exponent. This originally could have been written as 2 to the 1/2 in the denominator, so we would know that that is irrational. You also need to know your properties of exponents. If we have x to the third squared, that's x to the sixth, because we have two groups, and in each group are 3 factors of x. But if we have x to the third times x squared, that's x to the fifth. We add those exponents because we're multiplying like bases, so we have 3 factors of x times 2 more factors of x. It's important to remember these rules when you are working with rational exponents. Finally, we need to know how to convert between radicals and rational exponents. So x to the 1/2 is the square root of x to the 7/5 is the fifth root of x to the 7th. Although this form would be simplified, we know that in radical form, we often have to go one extra step. So we'd have x times the fifth root of x squared, because we would pull out an x from the x to the fifth that's inside, and we'd be left with 2 more factors of x. Let's look at a few examples where we are simplifying the same base with different indexes. When I see a square root times a fourth root, I know that I can't simplify them as is in radical form. However, I can rewrite these as rational exponents and work from there. Since the first one is a little more basic, I did it out first. So we have a square root of 2, and a fourth root of 2. So I wrote them with rational exponents. In order to put them together, I need to add the exponents. You don't have to show this step. You might know what 1/2 plus 1/4 is. It's 3/4. And since the problem was given in radical form, I rewrote my final answer in radical form, and either of these are correct. The next problem is similar. My first step still involves writing my radicals as rational exponents because we start with different indices. And once I get down and I add my exponents together, I get x to the 11/6. This would be a fine answer if we were working in rational exponent form. But when I convert this to the 6th root of x to the 11th, I know that I have an extra step here. I have to still simplify by taking out an x and then leaving the 6th root of x to the 5th. One thing you could do that is sort of like working with rational exponents is you could look at this and say, well, what if we just manipulated this at the start? If I changed this instead of a square root to a fourth root, then I could change this to a 2 squared instead of a 2 to the first. As long as you're multiplying the index and each exponent by the same thing, you're essentially just working in your head with this fraction and making it 2/4. So from there, then I have the fourth root of 2 squared times 2, or the fourth root of 2 to the third, or 8. This is just a different way to think about it. It's basically the same thing, just without writing out all of the steps. Now I will actually go through 2 of the type of problems that you'll see. I'm going to go through number 20 and number 23. I typically go in this order: simplify, rationalize, check form. So the first thing I'm going to do is I'm going to write my radicals with rational exponents. So I have 2 to the 1/3 over 4 to the 1/4. Since I know that I want these to have the same base, I'm actually going to make it 2 to the 1/3 over, this would be 2 squared, so 2 to the 1/2. I simplified that 2/4. Now I'm going to simplify. So I'm going to make this have a common denominator for my exponents. So this is to the 2/6 and this is to the 3/6. And then I'm going to simplify, and I'm left with 1 over 2 to the 1/6. In other words, I knew that I wanted to subtract my exponents, but in order to subtract them, I needed a common denominator. If you could do the 1/2 minus 1/3 in your head to get 1/6, by all means do that. So I've simplified. Now I need to rationalize. I know that I have an irrational number in my denominator because I have a fractional exponent. So I need to figure out, what do I need to multiply by so that this 1/6 becomes the next whole number, or 6/6. Since I'm multiplying like bases, I'm really saying, what do I add to 1/6 to get to 6/6? And that is 5/6. So I have 2 to the 5/6 over 2 to the 5/6, And my answer then is 2 to the 5 6 over 2 to the 6 6, which is just 2. This is your final answer. In this particular case, you could have rationalized the denominator first and then simplified, but in a lot of cases, you'll end up doing extra steps then because you will end up having to simplify whatever is in your denominator. Notice that you might think, oh, I have a like base here, but if you were to actually simplify this 2 to the 5 6 and this 2 to the 6 6, then we'd just get back to here. So as long as this fraction is less than 1, you're good. Here's a side note. So as I said before, I like to simplify, then I like to rationalize, then I like to check my form. So if I simplify this problem first, then I get 2 to the 4/3. I'm already done. If I rationalize it first, then I have 2 to the 2/3 over 2 to the 2/3, and that gives me 2 to the 7/3 over 2. But since this 7/3, I can subtract 3/3 out of it, I'm still not fully simplified. So I would need to subtract those exponents to get 2 to the 4/3 over 2 to the 0, or just 1. It makes more sense in more cases to simplify your exponents first and then rationalize the denominator so that you don't have extra simplifying steps later. Both ways will still get you the right answer. I'm going to do one more problem, number 23. I might need some space for this. In this problem, I start with rational exponents and radicals, so my final answer can be given in either form. The easiest way to do this problem is to first rewrite everything with rational exponents. Then we want to simplify. Basically, that means that we're subtracting our exponents. So in order to do that, I need to make a common denominator for my like bases here and for my like bases here. Now that I've done that, I can subtract. So I end up in the numerator with getting x to the 17/12, and in the denominator, I have y to the 37/15. I know that my denominator is not rationalized, so I need to figure out what I can multiply or what power I should put on y to get this 37/15 up to the next whole number. So my multiples of 15 are 15, 30, 45. So I say, oh, well, if I multiply 37, or if I add 8/15 to 37/15, then I'm going to rationalize my denominator. And that gives me this: x to the 17/12, y to the 8/15 over y to the 45/15. I'm going to write that as y to the third, and I can see then that my denominator is in fact rationalized. And my numerator can be left like this. Since the problem originally had rational exponents in part of the problem, I don't need to change this to radicals. If I did need to change it to radicals, I would then have to double check, and I would see that since I have an improper fraction here, I would actually have to further simplify that radical when I get there. I would also always check for absolute value. I would not need absolute value for this problem because I have an odd index, and here I have an even index, but the exponent itself started odd because this would be the fourth root of x to the 7th, so I would not need to check for absolute value. As I stated at the beginning, there are several ways to approach this problem. I personally decided to write everything with rational exponents, then simplify, then rationalize the denominator. You can choose to do it in another order, but this often requires the fewest number of steps. Let's look at this question. It says, think about it. Why is the expression 8 to the 7/4 over 8 not considered simplified, but the expression 8 to the 5/7 over 8 considered simplified? Because we have an improper fraction up here, that means that I could actually subtract out 4/4 from this exponent. In other words, I could divide the numerator by 8 and divide the denominator by 8, and that's going to give me 8 to the 3/4 over 1. When I divide, I'm really subtracting the exponent. If I were to try to do the same thing here, I would end up with a negative exponent or an exponent in the denominator. That's a fraction. So I would then have to rationalize the denominator, and I'd end up with this again. In these problems, you have the option to choose what method you want to use. You can use radicals, as I did on the left, or you can use rational exponents, as I did on the right. In general, if you are working within one term, it is often more efficient to use rational exponents. When I worked with my rational exponents over here, I actually did my fraction simplifying over to the side. I saw that I had y to the 4/3 over y to the 3/2, and so I did 4/3 minus 3/2 and got negative 1/6, so I immediately wrote my y to the 1/6 in the denominator. In either case, there are a lot of steps, but I would highly recommend that you use this method.